Okay, good morning. I always love Toronto in the fall because it looks really beautiful, all the colors of the trees. And there's yellow and orange, and some of them are still green. It's just a very colorful city. So today we're finishing off chapter 6, which is the whole momentum impulse chapter. We're going to talk a little bit about rocket propulsion. There's a new equation we're going to derive for that. I wanted to thank David for being the ed reader. So as you know, there's this discussion board, and I had planned to monitor it during class, but the problem is I just have too many computers up here. I have 1, 2, 3, I can see 4 screens, 5 screens, and I just get so mixed up. So David's gonna look at it under classes and shout out if there's any particular questions that he thinks are valid. So I don't want to put any pressure on any volunteers here. I'll sort of keep an eye on them. Ed Reader chooses what to read or skip. Read all of them if he wants. Paraphrase is fine. If you don't like it, you can always just volunteer. Got a few blank spots left, although I think the Halloween one just got filled this morning. So again, thanks very much. Yeah, so term test 1 has been marked. Average was 67%. That includes, everyone got or not everyone, but 95% of you got a +1 bonus mark for following the instructions, and I'll talk more about that and what happened to the 5% who didn't. And it's sort of a weird bimodal thing, a peak in A and a peak in C and a dip in B, which is a bit weird. Sometimes that happens like on the first test because there's sort of there's people who did a lot of high school physics and people who didn't, and sort of that sometimes splits it up because this is a lot of review for some of you. Median is higher than the average because of this big long tail off on the left there. 32 of you got perfect scores, and so that you didn't get the bonus point if you got perfect. You just held it perfect. So, and about 32% of you, about 268, are already in the A range, which usually only kind of can go up if you average it with the homeworks and the practicals, which are pretty high as well. You're not going to get it handed back to you. You've got that scan, which is emailed to you yesterday. So check your UToronto email. There were actually, since there's 2 scans, April did it separately. One side was the bubble sheet, the multiple choice. The other side was the long answer. So you get 2 emails, one for each. Take a look. So I actually posted not just the solutions and fully worked out solutions and video and all that stuff, but I also posted the same rubric that I gave to the marker who marked that thing at 8. So take a look at that. Make sure everything looks all right. If you've discovered there's been any kind of mistake in the marking, please let us know and we'll fix it as soon as possible. Whoop. I don't think this is an opportunity to have a big debate with me about the marking rubric, although you can if you want. Our effort here is to make sure everyone is treated equally and that there hasn't been any kind of mistake in your specific case. So, but I'm willing to talk about anything. Yeah. So this bonus point. So what you were supposed to do is write bubble your answers in on one side and write the long answer problem on the other side. You were allowed to write in the question booklet, and this is going to be the same for the term test 2, the same instructions for the final exam. So. But that's your rough work, and the first thing we do is discard the question booklet after the test, and we just keep your answer sheets. So you got a 1 point little bump if you did that. But there were 48 students who lost the bonus point because you had a blank written answer side. So maybe you didn't turn it over and you didn't notice that you were supposed to do it there. So normally you'd lose all 8 points, and that's, I guess, what's going to happen in test 2 if that happens. But this is the first test, and April very kindly decided to hunt through all the question booklets and see if anyone had written the written problem on the question booklet. And she did match up a lot. Sometimes people put their name because they figured out, hey, I have no name on this thing. And this was only done if you left your written answer side completely blank. If you put some stuff on there, then that's your official submission and you get the bonus point. If you left it completely blank, she hunts around and sees if she can give you some of those points back. But there's still a box of about 18 that are left that we weren't able to find it. So if you want to kind of meet me in office hours or something like that, and if you think you were one of the 18 students that just got a 0, but you wrote it somewhere, maybe you can identify your own handwriting or something. So you don't get the bonus point, but you could get the 8 points, I guess. Okay, where's my notes? My notes are way over there. All right, what's next? Should we do learning catalytics? Get things started? Question 1. We talked a little bit about, there was a truck and a bale of hay. I don't know if you remember that. We talked about a bungee cord stretching. So this is an airbag. How does the airbag, what's the physics behind how an airbag saves your life? Everything's looking over on the... Okay, do you see a good answer? Going once, going twice. Let's stop the survey. Stop delivery. Survey is saying 83% of you are voting for C, that it lengthens the stopping time interval, the delta T, for the passenger, and therefore, if that's larger, you can have a smaller force. And by the way, it's not just David who can yell at me. Anybody can yell at me if you want. That's still okay. So yeah, let's see. Before there was some speed. After, you have to go to 0. So there's a fixed impulse you need. You have a certain mass, you have a certain delta P, so the change in velocity times your mass, that's the impulse you're going to have to receive, because you're going to have to stop, because you just hit a tree. But the question is, do you want to have that F times delta T? Do you want to have large F, small delta T, or larger delta T, smaller F? And that's the force on your rib cage or something like that that's going to really hurt you, right? So that's why the airbag. Yeah, question? Yeah, that's a good question. So if you hit, so how much does it increase delta T? I don't know, but I mean, if you hit the plastic, I guess the dashboard or the steering wheel, that's hard plastic, and so it will bend a little bit, and that'll take a little bit of time for it to bend. But if you hit an inflated sort of pillow, it'll bend a lot more, so there'll be more time. I don't know what the factor is. It's a really good question. They must measure it with those crash test dummies. But it's enough to save your life, for sure. Okay. Any other questions? You're good? No? All right. Okay. Yeah, so this is, again, this impulse. It's not just that P initial equals P final, although it does if there's no external impulse. What the textbook does is add on the left-hand side of the equal sign the change. And we're going to do this exact same strategy for conservation of energy in Chapter 7, which is you've got energy initial plus the change in energy equals energy final. And this is what we're seeing here. We've got initial momentum plus whatever change equals the final momentum. That's how I'll tend to set up my equations in these examples. So, want to do an example? As part of a safety investigation, two 1,400 kilogram cars traveling at 20 meters per second are crashed into different barriers. Find the average forces exerted on A, the car that hits a line of water barrels and takes 1.5 seconds to stop, and B, the car that hits a concrete barrier and takes 0.1 seconds to stop. So in both cases, you've got a car and a barrier, and it's got some wheels or something. It's moving along at some V. This is initial. And maybe plus X is to the right. And then the final situation is that it's crashed, it's stopped. And V final equals 0. Again, this is the barrier. This is the car. And the mass of the car is 1,400 kilograms. And you define, I think what I'll do here is just define the system as just the car. The barrier I'm going to take as being an external impulse on the car. So that's important for how we're going to set up this equation. The system is the car. And the idea here is that delta T is different for the different barriers. Okay. And the barrier here is external to the system. So it provides an impulse. So in the simplifying diagram stage, you've got something like some initial momentum plus some impulse, these should have been equals 0. So your P initial X, which is positive, plus a negative J X equals 0. This is your P, that's the P final. Okay, so this is a negative impulse. So that's how I'd represent it with those momentum bar charts that she recommends. And so you can just write this down. This is the mass times V initial X, and it'll be minus the force times delta T equals 0, and solve for F. You've got F is just equal to M times V initial X. That doesn't change, but divided by delta T. So for A, you have F is equal to 1,400 times 20 meters per second divided by 1.5 seconds, and you get, I got 19,000 newtons. And for B, I've got the same equation, but now it's 0.1. 1,400 times 20 divided by 0.1 seconds is 280,000 newtons. Greater force for the concrete. So So that's sort of how the 4 steps look like for a typical impulse question. Okay. Next week in practicals, we're going to set up I guess a verification of this impulse momentum theorem. So the impulse momentum theorem, again, remember, is that if you do the area under a force versus time curve, then that's, or you do the average force multiplied times the time, then that's the impulse. And the impulse momentum theorem states that that should be the change in momentum. Well, we can measure both of these things. So you're going to have 2 sensors running simultaneously. You have a cart with a force sensor attached to it and a bumper on the end, which is actually this metal clamp. And the motion sensor, which you've used before, measures the distance as a function of time, so it plots position versus time. You can get the velocity from that graph by that slope. And then your force sensor will measure the force as a function of time and plot those things. And they're running simultaneously. You just sort of push it down the track, let it go, let it collide, and the entire thing that you're analyzing is just the collision. The momentum of the cart just before the collision and just after the collision, it'll be different, and you'll have a change delta P, which you can measure, because I think you can measure the change in velocity, and there's a scale in the room, so you can measure the mass of the cart. So you can get change in momentum that way. And then also, I'll just note that there is there's an integrate button. So if you drag the cursor on your LabVIEW code there, and you click on, your TAs will clue you into this, but if you click on integrate, it'll give the area of the spike. And so I'm going to do an example right now where i.e. Jx is equal to negative 1.1 newtons times second. So just going back a little bit, the force sensor is set up so that negative is push and positive is pull for whatever reason. So you'll see a negative, it's a negative spike because what's happening is that the force sensor is pushing when it's bouncing off that clamp. But that's okay, because you're actually changing the momentum from, if it's positive, if you've got the motion sensor set up on the opposite side, then you'll see it's going away, and then it's positive velocity, and then it's returning with the negative velocity. So my question here is that if you measured the cart to be 0.5 kilograms and it's traveling, you know that it's just before the collision, it's going at plus 1.2 meters per second. And you get this particular area of negative 1.1 newtons times seconds. The question is, what do you expect would be the final velocity of the cart? Now, in reality, you can actually measure this as well, but let's do it as more like a test question. In practicals, what you want to do is measure the uncertainties in both, and then see that the 2 measurements are consistent with each other, right? Within uncertainties. Okay, so initial. You've got the mass of the cart is equal to 0.5 kilograms, and you've got V initial x is plus 1.2 meters per second. And let's define the system. Here is just the cart, and then that impulse will be external. So the final V final x is what we're looking for, question mark. And we know that Jx is equal to negative 1.1 Newton seconds. So it's again, same sort of thing. You've got P initial x, but plus some negative Jx is equal to, and now it's going to be returning, so you've got actually P final x. So actually this should be, I guess, more negative than that other one. So mc times v initial x plus jx equals mc times v final x. Solve for v final x. V final x is equal to v initial x plus jx divided by m of the cart. So that's 1.2 is the initial, minus 1.1 divided by 0.5, which is your mass. So you would expect negative 1.0 meters per second from the impulse momentum theorem. And that's something that you can verify with your actual measurements next week. So the cart, it's interesting, the cart bounces and loses some speed. So momentum is transferred from that clamp into the cart. So there's an external force over some time. But before and after this collision, that cart now has less speed. So what that's going to mean in terms of Chapter 7 concepts is that there's some energy lost. We're going to talk about kinetic energy next time, but let's do another learning catalytics, shall we? A very bouncy rubber ball is dropped from a certain height and hits the floor with a downward speed v. Since it is so elastic, the ball bounces up with approximately the same speed going upward. Which of the following statements about the bounce are correct? And I think I'll let you read through that, chat with your neighbor, and give you a minute to click in. Well, you guys want to click in something, and we'll see what... I've also lost one of these. Okay. 5 seconds. 4, 3, 2, 1. Let's see what the survey says. Looking at 81% voted for B. The magnitude of the ball's momentum was approximately the same just before and after the bounce. So that's really what I was trying to say here, is that it's a vector. So the momentum has definitely changed, and there's been a big external impulse on the ball. But what's sort of interesting is that the size of just the magnitude of the momentum, which is related to the speed, has not changed too much. And that's why it comes back up to the same height. So why is that? Let's actually, here, I tell you, just press octplate. That's the one. Yeah. So here we are with these two rubber balls. So they're two like identical rubber balls, right? And you drop them. Okay, so they're not identical. So they're called the sad and happy balls, and you can sort of mix them up, and you actually can't tell which one you're holding, I think, until you pretty much drop it. And one of them is like a ball, and the other one, this one, has some way, it's made of something different so that it just doesn't want to bounce. It's kind of a strange, that's the sad ball. Oh, this is the happy ball. Okay. So Two objects, same mass, strike a flat tabletop. We also did this last time with I guess it was the clay or the putty ball and the rubber one. In scenario 1, the object bounces off the table, but in scenario 2, it stops when it hits the table. So what did I call that? I called that happy and sad. I don't know why. I shouldn't personify these things, but what I'm thinking there is that for whatever reason, due to something about the collision, the impulse is going to be twice as much on the happy ball as opposed to the sad ball, because they both have to stop, but the happy ball has to not only stop, which takes some upward impulse, but it also has to reverse its momentum and end up with a positive momentum, so that's double the impulse. But why? So this is a chapter 7 concept, which is called elastic versus inelastic collisions. But the basic idea is just that something has changed about the internal energy. So in an elastic collision, the ball has not changed, and nor has the surface. So sometimes there's a compression of the material, an elastic compression, so I guess all the molecules get a little closer to one another and they repel one another more. But then after the collision, they resume their original shape without generating much heat and without generating a lot of damage. In an inelastic collision, then the object, either the surface or the ball itself, is able to deform and change somehow, either generate internal heat because of the material it's made out of, or rearrange the material, making a big dent in it or something. And that takes energy, and so that takes away from the energy before and after. That's all I want to say about that. And any questions? I can tell you, I've been teaching in this room since 2004, and I've tried so many. I've tried the paper airplanes. I had a Twitter hashtag which had like obscene things on the. I've tried so many ways of trying to generate discussion in here that have all crashed and burned. So yes. So what, if the elastic collision, if it retains all its energy, then why does any ball you see bounce less and less? That's because it's not elastic. Every collision is inelastic in real life. It's just there's degrees of inelasticity. So there's something called in physics a perfectly elastic collision, which would be when you drop the ball and it comes up to exactly the same height that you released it from, which never really happens. But it's called a perfectly elastic collision. And it would keep bouncing forever, I guess. A little hard to picture. But it's like the frictionless, it's one of these situations where you can imagine it. Is that our splitter? Yeah, there we go. So I had jet propulsion. So cars change their velocity because of an external force of static friction on the bottom of the wheels. And a ship, I guess what's happening is the ship pushes backward on the water, and the water pushes forward on the propeller of the ship, and that's what propels a ship forward. So you've got some external objects there that are acting on a car or on a boat. But a rocket, way out in empty space, has nothing to push against. So how can it possibly go? And it is possible. We certainly send rockets out into the solar system that are far, far away from the Earth or from any other objects. Even the International Space Station has nothing to push against, and it still has some navigation ability. So what you do is you have fuel, and the fuel gets expelled somehow as exhaust, and it's the exhaust that you're pushing against to get yourself going. That's how rockets work. Burning fuel is ejected backward at high velocity, so the rocket ends up with a forward velocity in order to conserve momentum. So there's no external force needed to propel a rocket. So, okay, it gets a little hairy. Okay, let's first do this. because the rocket equation is a little bit nasty looking. But let's think of how we could, with neglecting any force from the water or neglecting any force from the air, you're just in a boat. I guess there's going to be normal force and gravity, but those will cancel out because there's no vertical acceleration. With no horizontal forces, you can move a boat. And so my idea is that the person to the right throws the ball to the person on the left. So there's two things. What is the direction immediately after the ball is thrown? The direction of the boat's motion. Immediately after the ball is thrown, first thing. And then second thing is after that ball is caught on the other side. So in between, I guess the ball is in the air. Yeah, question, David?
There's a question. Will we be working with examples where there are external forces acting on the system, and we need to consider those in our calculations?
Yes, that's a great question. So absolutely, this is going to be an example where there's no external forces, but a lot of those ones, like even that the practical question with the collision cart experiment, we treat that as an external force. It all depends on how you define your system and whether or not you have an impulse. So this is a zero impulse situation, and rockets are a zero impulse situation. So, yeah, so that's right. So P initial is P final in all these, in whenever there's no external impulse.
Professor, there's another question. When is impulse negative and when is it positive?
Well, that's a good question. So when the external force is negative, the impulse is negative. When the external force is positive, the impulse is positive. Because the force is a vector, and you always have to define your direction of positive and negative. Liking this. You have 30 seconds to click into this question. Starting now. Hoverboard here. Whoop. Okay. Going once, going twice. For this one, it's almost just as hard to read all the answers. Some of these things, but I think if you read it really carefully, A is good. And it's a conservation of momentum idea, is that while the ball is in the air, it has a momentum that is to the left. And so the boat, which is the other part of the system, if you define the system as being the boat, both the people and the ball, the boat and the people have to have a momentum to the right to compensate out, so that they sum to a zero momentum situation. You guys want to go through this rocket equation thing next? Yeah, this is thrust. Thrust is the force exerted by the fuel on a rocket during jet propulsion. It can be like a million newtons. It can be pretty high. That's how you get these things to go up to space. It provides an impulse which changes the rocket's momentum. So, and the same principle works when you blow up a balloon. You can do that. Just twirled around, but basic, you've all done that, right? So that's the same exact thing. So even in a vacuum, the balloon would go away because you've got air going backwards and the balloon going the other way. And the way she draws it is the system is the fuel plus the rocket, and it might start off with some initial zero velocity, and then afterwards the fuel moves to the left, negative, and the rocket moves to the right. So there's actually zero initial velocity, zero initial momentum, zero external impulse, but at the end you have equal momentum for the fuel, positive momentum for the rocket, negative momentum for the fuel. And then in order to derive this equation, we're going to generalize it a little bit more by allowing the rocket to have a little bit of initial velocity. So if the rocket has some initial velocity, and then the fuel comes out, then by conservation of momentum, you can rearrange this to find the mass of the rocket times the initial rocket speed minus the final rocket speed. And so these are velocities, by the way. So that's actually initial minus final is negative of the delta v. So you've got delta v is, if you put the negative sign on the other side, negative mass of the fuel times the velocity of the fuel in the x direction divided by the mass of the rocket. So, and then we do a trick. It's a calculus trick, but you divide both sides by delta t, and you get delta v divided by delta t, which is our definition of average acceleration, is equal to this negative mass of the fuel times the velocity of the fuel divided by mass of the rocket times delta t, the amount of time that has passed. So this gives us an equation. Just put that over to the right, to the left there. In this equation, the mass of the fuel is going to be the change in the mass of the rocket. So the rocket will decrease its mass a little bit because it's lost some of its fuel as exhaust. And we can also write V final of the fuel, or V fuel final x as the velocity of the exhaust. And this gives us an equation for the acceleration of a rocket when there's no external forces on it, which is acceleration is velocity of the exhaust divided by mass of the rocket times delta m by delta t. So the change in the mass of the rocket per time. And this should all work out to be meters per second squared. So you've got a kilogram on the top, kilogram on the bottom, and you've got velocity meters per second and divided by delta t. So that's called the rocket equation. We can use it in an example. Times it. Very good. Let's call this the rocket equation. Pretty handy thing to have in your aid sheet, because it's not that fun to derive it, but you can. Okay. Example. A rocket is fired in deep space where gravity is negligible. In the first second, it ejects 1/160th of its mass as exhaust gas and has an acceleration of 15.2 meters per second squared. What is the speed, v gas, of the exhaust gas relative to the rocket? So, again, I always like to sketch these things. So, there's the thing. There's the rocket. And there's this is v gas. This is question mark, we don't know. Mass of the rocket. This is acceleration of the rocket going forward. Acceleration of the rocket is given in this case is 15.2 meters per second squared. And it says that in delta t is equal to 1 second, delta m over the mass of the rocket is equal to 1 over 160. 160th of its mass gets ejected. So if you do mass of the rocket divided by 160, that's delta m. That's another way of looking at it. And so let's just check our assumptions. Momentum is conserved because there's no external forces. Okay, so because no external forces. So that's an assumption there. It's part of my reasoning so that I can use the rocket equation. Which is that AR just equals V exhaust, or V gas, they're the same, divided by mass of the rocket times delta M divided by delta T. So we're just going to solve for V exhaust, which is the same thing, because the exhaust is the gas. Let's call it V gas, is equal to the acceleration of the rocket times m of the rocket divided by delta m, I think, times delta t, when I rearranged all that stuff. So I've got 15.2 meters per second times 160 times 1 second. So I've got V gas is equal to 2432 meters per second. Maybe call it 2400. Something like that. Pretty fast, but that's what you expect for rockets. Okay, times it now. Okay. Should we do one? I think we have time for one more example. Which is a pretty good one. Let's do the car collision example. So this is an idea that you're. So there's a car accident, which is a yellow Hummer is driving south, and it collides at an intersection with a blue Toyota, which was driving east. And both roads have a speed limit of 50 kilometers an hour. And what happens is after the collision, the cars stick together. And the combined mass then skids along the ground. So the police come, and what do they see? Well, they see this crumpled mass of Hummer plus blue Toyota, and they see these skid marks, like that black, part of the tires of the road have left this big streak on the road, and it's 10 meters long, and it's angled at 32 degrees east of south. Okay, so you can imagine that from above. And we also know that the coefficient of kinetic friction between rubber and the road, because it's sliding now, when this is sliding friction or kinetic friction, the question is, how fast were these cars going before the collision, and was one of them or both of them speeding? So who's at fault? So you're going to be the police detective and use your Physics 131 skills and solve this out. So what we're going to do is first assume no external impulse during the collision. This is the, what was it called? The impulse approximation, which is that during the collision, what's important is so J is equal to 0, so P initial equals P final. What's important are the internal forces of the system of the car plus the Hummer, is that the Hummer pushes on the car pushes on the Hummer, but those forces are much, much greater over that little delta T than the friction from the road, for example. So we're going to neglect the friction of the road during the collision, and then after the collision, we're only going to look at the kinetic friction of the road as it's sliding. So there's two segments of motion. One is the collision, and it's got two actual components, is X and Y. Actually, let's do this. I'm getting mixed up here. Let's sketch it out first. I forgot to sketch. Let's sketch initial. There's the Hummer going south. There's the Toyota going towards the east. The mass of the Hummer is equal to 3,900 kilograms. And we can define, let's define plus y is north, and we'll define plus x as being east. And so Vy is what we don't know, but it's negative. We know it's negative because it's going south. And then the Toyota, mass of the Toyota is equal to 1,200 kilograms. And the velocity x is what we don't know, but we know that it's positive. And then finally, We've got, I don't know how you could draw them kind of crumpled together. There's Hummer, there's Toyota. This is a combined mass. This happens a lot in these inelastic collisions. Mass of the combined mass CM, I guess, equals the mass of the Hummer plus the mass of the Toyota. And it's got some velocity, v final, of the collision. And what was said, and this is going to be v initial, of the skidding motion, it said that it's 32 degrees east of south. So this is your theta, is 32 degrees. And you can tell that by looking at the skid mark there. So the idea, what we're going to do, is that kinetic friction, I hear all this giggling every time I say the skid mark. Okay. Friction causes the combined mass, CM, to slow as it skids to zero. So basically, you've got some V initial, and then it's going to go a distance 10 meters, and then it's going to stop. V final equals 0. Sorry, it's a little squishy there. So we've got two segments of the motion. You've got the collision followed by the skidding. And it's the same thing we've done before. The final of the first segment becomes the initial of the second segment. V final of 1 equals V initial of 2. So let's start by analyzing segment 2, actually, because that's easier. We can use kinematics equations. Segment 2, which you've got, let's do a force diagram from above of the combined mass. You've got, you've got the normal force of the road on the combined mass. You've got the gravity force, mg, and combined mass g, and you've got this kinetic friction force. And this is actually where you've got plus y, I guess, is up. And this is d, direction of the skid. So what I'll say is that the forces in the y direction there is normal minus m combined mass g. So you get the normal force is mass combined mass g, and you get the sum of the forces in the d direction is negative mu sub k times n. So it's going to be negative mu sub k times the mass of the combined mass times g. So A in the d direction is equal to that net force divided by the combined mass. You get negative mu m combined mass times g divided by combined mass. This is where the masses cancel. It's always lucky. And you get, and then you can use equation 2.7. 2 times A times D equals V final squared plus V initial squared. So I think I'm going to, bizarrely enough, leave it there because I have run out of time. Next time I want to finish this and try to determine who was speeding, the Toyota or the Hummer. And we can actually, maybe we'll do those next time on the thing. I just didn't time it all that great. What I'll say, I wanted to do one more thing, which is just let you know for the weekend, something to think about, is that we're going to talk about work and energy. So if you're carrying a bag and you carry it along some distance and you're applying a constant upward force to it, what is the work that you're doing on the bag? That's something to ponder over the weekend. Have a great one, and I'll see you here on Monday. And thanks again so much, David, for those questions. It's awesome.